Hello, my name is Pramod Varshney, and I'm delighted, along with my co-presenters, Pierluigi from Norway and Domenico from Italy, to be presenting this tutorial, Signal Processing for IoT, Decision Fusion and Sensor Networks. We will be presenting it in 3 parts. The first part I will be presenting. I'll be followed by Pierluigi and then Domenico. So let's talk about the part that I'm going to be doing. So I will be presenting some fundamentals on distributed detection and decision fusion. And as I said earlier, I'm from Syracuse University, Syracuse, New York in USA. The outline of my presentation that I will be giving a brief introduction. Then I'll talk about signal detection as a hypothesis testing problem. And this will be a review for most of you because this is basically what one learns when one takes a course on detection and estimation. Then I'll move from there to distributed detection. Then a part of that distributed detection is fusion rules. Couple of important considerations within distributed detection. Basically, we will be talking about statistical dependence of observations and security aspects, namely operating in the presence of Byzantines. I will have an extended list of references at the end, so you can try to look for it at the end. So the reason that I have this picture is that this is the sensors conference, and sensors are everywhere, and they are being used in different applications. They are being used in health, they are being used in manufacturing, agriculture, and you name it. So essentially, it's sensors, and the signals coming out of them, processing of them is something very important. Some other applications are autonomous cars, where a number of sensors installed on the car, they try to determine how to avoid obstacles, how to stay in their lane, and those kinds of things. The next application is drones, which essentially what you have is you have these unmanned air systems, and they will be doing some sort of, in this case, some reconnaissance. They're trying to figure out what happened after a military exercise, but there are many, many applications of drones that are being used and planned. Finally, coming to the Internet of Things ecosystem, and this will be presented more by my co-presenters, but the idea is that you have applications in terms of, as I said, smart cities, smart grid, connected vehicles, and you name it. The underlying technology is wireless sensor networks, and they try to solve certain inference tasks, such as detection, classification, estimation, and so on. This tutorial is focused on the detection problem, and I'll talk about it as I proceed. So first, we give a very brief introduction on signal detection. So this is the textbook thing that we all studied, or most of us studied. So in this problem, the idea is that you are trying to figure out the presence or absence of a certain phenomenon or certain information pattern based on some noisy observations. So the process that we are trying to accomplish is through a probabilistic framework, and the probability or randomness is coming due to noise. So we use statistical decision theory, statistical principles, and based on those, we try to determine the presence or absence of any phenomena. And this is the problem of statistical inference. It could be more general than the detection problem. We could be doing estimation, classification, and so on. And they all fall under the general inference problem. Sample applications, IoT, as we briefly discussed, but one can do biomedical signal processing, radars, communication theory, cognitive radios, and you name it. There are many, many applications where signal detection plays a major role. So this can be formulated as a hypothesis testing problem. So essentially, if you have a phenomenon, theta, and it can take a finite number of values, or it could be in a finite number of states, and each value corresponds to a particular hypothesis. So maybe if we have two values, 0 and 1, they could be like corresponding to H sub 0 to hypothesis 0 and hypothesis 1. And the idea is that after observing, receiving an observation, you want to determine which of these hypotheses is true. So here, the first thing that I'm talking about is a binary hypothesis testing problem. So you're trying to figure out a yes or no type of question. Or theta, it takes values theta sub 0 and theta sub 1. So which one of these is true? And here, H sub 0 denotes the hypothesis that theta 0 is true, and H sub 1 denotes the hypothesis that theta equal to theta 1 has occurred. So these could be presence or absence, yes or no, etc. Now, we don't have to have a binary problem. We could have an emery problem. So there could be m possibilities. And in this case, the hypotheses would be denoted as H sub 0 to H sub m minus 1. There are the two types of, broadly speaking, hypotheses. Simple hypothesis, in which theta sub I is a fixed value. Composite hypothesis, where theta sub I belongs to a range or interval, things like that. In this example, it shows that theta sub I is between -1 and 1, for example. Now, the goal, as we said, is detection. So what we need to design is a detector, d of x, x is the observation. And based on this rule, basically you try to decide H sub I if the inference is theta equal to theta sub I. So this is what we are trying to determine, this d, this function d. And what it does is that it partitions the observation space into m regions in the case of emery hypothesis testing, and 2 regions for binary hypothesis testing. And then the probability of detecting H sub I when true hypothesis H sub j, that is denoted as P sub ij. Notice that there is a possibility of error, and the reason is the randomness, the noisiness of the signal that we are observing. And because of that, we deal with the problem in a probabilistic or statistical framework, and there could be errors, and we'll talk about that in a minute or two. The risk of decision making, meaning that H sub I is true, and we decided or we declared H sub j, then how much does it cost? Because we need to be able to have some sort of a decision making. I mean, so C sub ij represents the penalty of making the decision H sub I when H sub j was indeed the true hypothesis. And one can talk about the total risk or conditional risk and the average risk. I'll come back to it in the next slide. So assume that we have a binary hypothesis testing problem. Then the average risk associated with this binary decision-making problem is given here. And pi sub 0 and pi sub 1, these are prior probabilities. And these P sub ij's we had defined earlier, and the C sub ij's were also defined earlier. So, so essentially, this is the cost, and we would like to minimize this cost. And in order to minimize that, we can come up with a decision rule that P11 divided by P sub 10 is less than or equal to tau. Then we basically pick the hypothesis accordingly. So I'll let you look at it for a minute. Okay, so let's move on. So I guess what I'm coming to is that we have something called a likelihood ratio. And so likelihood ratio is this P sub 11 divided by P sub 10. So, so this likelihood ratio, so the decision is made based on this likelihood ratio, and the detector is based on this, which is given by if L of X, which is the likelihood ratio, if it is greater than the threshold, then decide H1, otherwise decide H0. So remember, we talked about the fact that the space, observation space, is to be partitioned, in this case, in two regions, and this rule partitions it into two regions. And then for convenience, in many family of distributions, such as exponential and Gaussian, we take the log of this, so log of L of X, and that makes life easier. And so D of X is, I mean, if it is greater than a threshold or less than a threshold, then we decide on H1 or H0. Okay, so let me move on to the next slide. So now we are moving. So this was the basics of detection theory, and this was a review. Now from there, we want to move to the problem of distributed detection. So in conventional detection theory, we were using a single sensor to observe our phenomenon, and we were trying to detect based on that. Now, in the early 1980s, we moved from this notion of a single sensor to have multiple sensors observing the phenomenon, and these multiple sensors working together and trying to make a decision regarding the same hypothesis, same phenomenon as before. So for instance, if we were dealing with H sub 0 versus H sub 1, we were still dealing with those two hypotheses, but now multiple sensors or multiple nodes collaboratively make a decision regarding that phenomenon. So we could be talking about centralized. In this case, all sensors, they collect the information at one place for decision making. So this is still the same philosophy, same kind of mathematics as the conventional detection theory, because all the information is available here. In decentralized or distributed detection, all the nodes, they receive their observation, and then they send some information, and we'll talk about what kind of information can be sent to a central fusion center that performs the fusion of information and makes the global decision corresponding to the hypotheses. Now, advantages of distributed detection: we have diversity, it makes things robust, reliability, so graceful degradation of performance, and coverage, we can try to cover a larger area. However, it comes with some disadvantages. There is communication overhead, and there could be malicious nodes that could be impacting, they could hack, or they could impact our decision making. So here is a picture. This is known as the parallel topology. So there is a phenomenon, and a number of sensors are collecting observations. They send some information, processed information, to a fusion center, and it makes the final decision. And we could be doing detection, estimation, etc. So first, I'm going to talk about detection without fusion. So let me go back to this picture. So this fusion center is not there. So you still have these sensors making the observations, and they will be making decisions D sub 1 through D sub k. However, so you might think that they can do it independently, but the way we do this thing is different from the conventional thing, is that we perform a network-wide optimization, meaning the costs associated with the overall decision-making, they depend on each other. And in this case, we know it as parallel distributed detection without fusion, because there was no fusion center. And then case one, the more general thing, in this case, the decision rule at each of the K sensors depends on the observation, and the decision rule at other sensors. So notice that observations need to be shared, which is quite a bit to ask. So the second thing one can assume, and it had been assumed quite traditionally, that the observations were conditionally independent. In this case, the thresholds used at the different sensors will depend upon each other. So the thresholds were dependent, but we didn't need to share the observations. Now let's move again to this distributed processing. So basically they send some sort of a local decision. to the fusion center. And then what we need to do is we need to optimize the processing that needs to be done here and the processing that needs to be here. And it is a system-wide joint optimization, and it's a complicated thing. So essentially what we need to do is we need to devise the processing here so that xi comes in and we come up with the d sub I. And at the fusion center, you are receiving k decisions, let us say, and you need to combine them and come up with the d sub 0. So in the work, like we will be focusing on binary quantizers. So this d sub I will be binary. And what we need to do is when these are binary, then what we want to do is we want to actually find out the overall design and some optimization criterion like Bayesian, for example. This problem is NP hard in general. So let's move on, and then the decisions made at the sensors that are sent to the fusion center, there are two types. One, soft decision fusion, and the second is hard decision fusion. In soft decision fusion, the sensors could be sending soft values. They could be observations directly, or you can quantize the statistic that you have in multiple levels beyond binary. You send them to the fusion center and it tries to combine them and makes an optimal decision. In hard decision fusion, the sensors, they send binary information. So 0 or 1, for example, they send, and then the fusion center has to decide yes or no at 0 or H1. And the complexity is lower, but the performance there is from between soft decision and hard decision, soft will perform better. Okay, now, in soft decision fusion, I mean, this is more like the standard communication problem, and one could be using things such as maximal ratio combining or selection combining. This is in standard digital communications, wireless communication literature. But if you have a quantized data that is coming from the sensors to the fusion center, then the likelihood values that we talked about earlier, it is mapped or quantized to finite discrete levels, binary if we are dealing with a binary quantizer. And the optimal decision rule then depends on the PD, that is probability of detection and probability of false alarm of the individual sensors. So probability of false alarm is probability that the sensor decides an H1 when H0 was present, and PD is it decides H1 when H1 was present. So these are the things. So they give the performance of individual sensors. So one could use in hard decision voting rule. So one can basically say if there are K yeses and nos coming, if L out of K are saying yes, then you decide H1, otherwise you decide H0. If K is equal to L, like if they are equal, then we are dealing with an AND rule. If L is 1, then we are dealing with the OR rule. And the overall probability of detection and false alarm are given by this. And so on. So this is how you evaluate the performance of the fusion system. So as I said, just to summarize again, the crux of the distributed hypothesis testing problem is to derive decision rules of the form, which means how does detector I or sensor I decide H0 or H1? And it is done typically by a likelihood ratio test. And basically, if the things are conditionally independent, then it's like one can show that it is the thing to do, it's optimum. And then at the fusion center, you need to decide a 0 or a 1 based on all DI. This DI should have been here. That's what it is. Now you can see that the fusion rule, if it is a binary problem, it's a logical function with k binary inputs and 1 binary output. So the number of fusion rules is 2 to the 2 to the k. So it grows very rapidly. Just for illustration, if we had 2 sensors and binary, then there are 16 fusion rules. And you can see that the 0, 0, like this one, is that no matter what the sensors are saying, you are always saying no. And here you're always saying yes. My usual joke is that when my kids, if they come and ask me for something, and if the answer is always no, then this is the tough dad, and this is a very lenient dad. No matter what you say, it's yes all the time. So anyway, so coming back to it, the base risk can be written in this manner, total average cost, and then the likelihood ratio test, we can express it like this. The computational complexity increases exponentially, as we had talked about earlier. And as far as the fusion rule at the fusion center is concerned, it depends upon the quality, the performance of individual sensors. And essentially what we do is, using a likelihood ratio test at the fusion center, the following expression comes out, and you compare this log L of X to a threshold. And if all the sensors are identical, then this rule, this decision rule, simplifies to the L out of K fusion rule. So if L or more sensors are saying yes, then the answer is H sub 1 and the decision is, otherwise it is H sub 0. So this is one of my very early PhD students, Zeno Shire. He basically came up with this fusion rule in 1985-86 timeframe. Okay, one question that you might have is that how is the performance of this? So there has been a lot of analyses, and people can show. So basically, based on Stein's lemma, one can show that it does go to 0, the probability of, like in this case, the false alarm, or probability of error. And Stein's lemma comes under information theory. If you have taken a course, you must have seen this. And what it is saying is that, and this represents the rate at which the probability of false alarm goes to 0. And this represents the rate at which probability of error goes to 0. This D is known as the Kullback-Leibler divergence, and this C is known as the Chernoff information. So there is a lot of nice theory behind it, and how the performance improves as the number of sensors or detectors increases. Okay, now I'm going to move on to two things. So until this point, we had assumed that the observations at the sensors were conditionally independent. But we all know that in many practical situations, that is not true. So we want to talk about this thing where you have a phenomenon, the observations are dependent, and here are the sensors, and heterogeneous. I mean, I really didn't mean to get to that, but essentially they could be heterogeneous. That's essentially what I am saying. And these U sub i's, they could be local decisions, as we discussed earlier. They could be features. It could be raw signal. So I want to spend 3 to 4 minutes on this problem. I mean, when you have conditional dependence. So, excuse me. So there are, I mean, how to define the dependence. So, I mean, all of us, we have used like correlation coefficients or mutual information based things and so on. And in our distributed detection problem, there was a nice paper, Sitsiklis in Athens. They talked, I mean, they showed that it is an NP-complete problem. And then the decision fusion strategies, a couple of people, well, these people in the early 90s, they talked about it. But what we did, we started looking at it again, the problem, and we used Copula theory. And this Copula theory is something that very nice. It was by somebody called Sklar. And this is a very nice theorem. And I'm going to go to the next slide where one can see it very easily. So what it does is that it allows one to represent the joint density. It can be written as the product of marginal densities, and this would happen if you had independence, and times a density which is called Copula density. So this is the thing that essentially brings in the dependence, how to characterize dependence, and this is learned based on training data. So here we are trying to learn the dependence. You can call it machine learning. And what it shows is that under the independent case, conditionally independent case, you would have had this part and you would have compared this to a threshold. Because of dependence, you have an additional term. And what I'm saying here is that Copula-based test statistic decouples marginal and dependency information. So this is something that Copula allows you to represent the decision rule in such a nice fashion, convenient fashion. And there is a lot of work, and I'll give you the references at the end. And this problem was, if you, at the fusion center, if the decisions, they are dependent, then the first part of the statistic is the original Chair-Varshney fusion statistic, and this is under independence. And then you have cross product terms if you have dependence, and then you can, again, this compared to a threshold, and you make a decision. Just as an illustration for one of the problems that we did, so if we had ignored the dependence, then the performance, so this is the receiver operating characteristic, or ROC, and this solid line would have been the result. But when we exploited the dependence, when we took it into account, we were able to improve the performance quite a bit. So this Copula-based signal processing, that is able to let you use statistical dependence and improve performance. The last thing that I want to talk about, the security aspect. So there has been a lot of work, a lot of it by our group, that you distributed inference if there are malicious nodes in the network. And so in this case, this is the same parallel fusion network. And if list B, for example, is a Byzantine node, so it's an inside the network node, insider, but it sends false information to try to disrupt the performance here. So, essentially your final decision, it wants to make it wrong. It wants to impact it. So the type of research questions that one can answer, one can raise, are what is the minimum fraction of Byzantine nodes alpha blind to required to blind the FC? By blinding the FC means that the fusion center is not able to extract any information from the incoming information from the sensors. Now, the sensors, they don't have to always flip their thing like in the binary case. So this question here is that what is the optimal flipping probabilities at the Byzantines to cause maximal damage to the performance? So what should the Byzantines do to have maximal damage? So this is like optimizing their negative impact on the network. Then there could be a game theoretic formulation. So the Byzantines are attacking the system, and the good guys, the honest nodes, they are trying to have a defensive strategy. How can we mitigate the impact of Byzantine nodes? Should we just try to find out who is a Byzantine and then ignore them, or are there better ways of doing this mitigation? And then if there are Byzantine nodes, if they behave like they want to be under the radar and they try to basically impact, they don't want to get caught, but they want to, impact the network operation. So there are many such research questions, and they have been done. And basically, I'll give you some references at the end, which is coming up. And I'll not talk about any more details, but I wanted to beyond decision fusion, beyond distributed detection, two aspects that are important that I guess I have some bias because we have worked on these quite a bit. So one was security. So if there are insider threats or you have Byzantine nodes, how to deal with them. And second was the statistical dependence if they're dependent the observations. So then I just want to give you a list of references. So these are the standard. The first two are on detection theory. And this book is based on it talks about the early part, the distributed detection part. Then I have a number of references on Copula Theory related work. There are 2 pages of this, of the references that I'm giving, but there are many more papers that we have. So you can go visit my website and find some other things. Something interesting I just caught my eye, that using copulas, we were able to actually make an impact in health care. So we were able to classify Alzheimer's disease better. So this was something which was quite an interesting thing that we were able to do. More work on Copula Theory related work, and you can look at my website for more details. And finally, these are some references on Byzantine related work, and there are many other papers listed on my website. So you have some that are in front of you, but as I said, there is much more that has been done. So I will end my part here and hope to see you on October 31. And so bye.